Perfect. Okay, so my name is Zach Shurep-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I would also like to introduce, well, my colleagues. I'm sorry, I'll go back on that. I'll introduce my colleagues and co-organizers, Andrea and David, but unfortunately they are not here today. So we're all from the Alan Turing Institute, and we co-organize the seminar series. For those of you who are not familiar, the Alan Turing Institute is UK's National Institute for Data Science and AI. So on a side note, if any of you are interested in sharing your work in any of our upcoming seminars, please feel free to get in touch with us, and we'll be happy to find a suitable slot. And now, as for the format of the seminar, our speaker today, Stefano, will speak for around 45 minutes, followed by a Q&A, which you may do so by asking in person or by entering the question through the chat. So without further ado, I'll introduce our speaker for today. And today's speaker is Stefano Castruccio. I hope I've pronounced your name correctly.
Good.
Yes, so Stefano has obtained his PhD in statistics in 2013 at the University of Chicago in the United States. He was a postdoc fellow at King Abdullah University of Science and Technology in Saudi Arabia, lecturer at Newcastle University in the United Kingdom, before moving to University of Notre Dame in the United States, where he is now associate professor. And his work focused on modeling spatial-temporal data for environmental applications with stochastic partial differential equations and stochastic machine learning models. Very much look forward to your work. The floor is yours.
Okay, well, thank you very much, Zach, and thanks for the Alan Turing Institute for the invitation to this talk. It's also good that I give a talk to European colleagues. It's particularly good because I don't get asked any question about football at the University of Notre Dame. That's the first question I got every time I deliver a seminar in the US. Also because in the UK, even the word football means a different thing. It's not American football, but it's actual football, what I would call football as an Italian. Anyway, all right, so today I'm going to talk about one particular class of models which we have been working on over the past few years with my research group, a stochastic spatio-temporal machine learning model. And in particular, I'm going to talk about how do we calibrate these types of models. I'm going to show you an application on citizen science data on urban air pollution in San Francisco. And later on towards the presentation, I'll also show you some more like follow-up work on spiking neural networks and physics-informed model, because as I understand, this is kind of like the main theme of the seminar series. So I'll add a few slides on physics-informed models. So briefly, I'll introduce neural networks in time. I'll do a presentation. I'll present neural networks the way I see them as a statistician, which may not be the classical way that computer science people look at the same kind of model. I'll introduce issue state networks, which are the type of the subclass of machine learning models in time that I will be working on. Those are a stochastic version, which allows to do uncertainty quantification. I'll talk about our main contribution on the first work, which is how do we do proper calibration and uncertainty quantification of these forecasts. I'll show you a simulation study to make the point that these models calibrated are basically as good as it gets. We compare them with all sorts of other models, both in the statistics and machine learning literature. I'll show you an application on the San Francisco air pollution data. And then, as I said before, I'll jump into talk about a little bit about spiking neural networks and physics-informed methods. If you want to know more about the details, we have one work which is in press in the Annals of Applied Statistics, and a couple of others which are under review. But this one here is already available. If you have any questions and if you want some preprints on the other ones, let me know. All right, so before I jump into the kind of technical details in the introduction of neural networks, just some motivation. I guess I don't need to introduce why do we need neural networks in general, but perhaps it's useful to say a few words about atmospheric science and climate science, because they're not nearly as popular as they are in image recognition or other fields of science and engineering. In particular, people have started to acknowledge the need of these kind of non-parametric and flexible methods such as neural network quite recently. And the reason is that if you look at, say, monthly data in the US, here I'm showing you on a map of wind speed, you can clearly see that there is a pretty regular and well-behaved pattern if you aggregate data at monthly level or daily, or annual level. If you were to show a global map of temperature at annual level, it would be relatively well behaved. You really don't need anything complicated to capture something like this. You can probably get away with a Gaussian process with some trend. If, however, you go at 5-minute scale, so very high resolution data in time, and possibly in space, then you start seeing all sorts of nonlinear self-replicating patterns, such as eddies, for example. Here I'm showing you a snapshot of a 5-minute window global, 5-minute aggregation of wind. And you can see there are all sorts of patterns here. And I mean, trying to capture these models with a parametric statistical model is quite a challenge. And in those cases, using this kind of non-parametric deep models, such as neural networks, will give you an edge. So really, the main motivation for using neural networks in climate science are to capture these very fine scales, very highly nonlinear processes, which occur at scales such as urban, which is the one which I will talk about in the application. So briefly, some notation. Y of t will be my vector of multivariate data. They could be spatial, they could not be spatial. It doesn't really matter as far as the methodology is concerned. And my goal is to do forecasts. So this is the classical textbook problem of determining the conditional distribution of y of t plus k, conditional on having observed all the data up until time t. And I want to solve this problem using a dynamic neural network or a recurrent neural network, if you are coming from the machine learning literature. So allow me to introduce first what do I think of as a neural network, because again, I will use a fairly different approach from the classical one, which is kind of looking at an algorithm and trying to minimize it. The way I see this as a statistician is that I have a non-parametric model, which is basically a generalized version of a linear model, except there is a new function g, which makes things more complicated and more flexible. So if you want to talk about, say, a shallow and Gaussian neural network, so a very, very simple neural network, I look at this problem as the following nonlinear regression problem. So g is some sort of nonlinear function, is the activation function. You are all familiar with ReLU, with the hyperbolic tangent, your favorite activation function. X is your design metrics. If you, again, I'm speaking with the language of linear regression, so the input of your problem. W is this collection of weights or of parameters, again, using the statistical words that you want to assess. And beta is the term which is mapping this kind of transformation of the input into the output space. And then I have an error, which is normally distributed with mean zero and with variance sigma squared. So this is the problem, the way I look at this, as this is a statistical model as far as I'm concerned. So if it is a statistical model, then I need to determine the estimators. I need to perform inference on the parameters. Now we know how to estimate W hat. There is a large suite of algorithms in Keras and TensorFlow. We know how to do backpropagation. These algorithms right now are fairly standard, so there is nothing really spectacular about obtaining the point estimate of the parameters. The problem is the uncertainty. How do we assess the uncertainty about these parameters? And again, there is a pretty large and growing literature in machine learning on Bayesian neural networks. You use variational Bayes, so it's a pretty complicated problem, but there are ways to get around it, especially in an approximate fashion. The problem with all these approaches is that when you're dealing with time series, especially high resolution time series like 5 minutes, you cannot do variational Bayes because I mean, you need a forecast in 1 minute or maybe 30 seconds. So you don't have enough time to develop, to do this kind of, even these approximate inference would just not work very well because they're not as fast. There may be cases in which they are, but here I'm making a very general statement. In general, variational Bayes is expensive and Bayesian neural networks are expensive, a time that we don't have if we want to have real-time forecast. So the main idea that I will be exploiting throughout the talk is to assume that instead of having a matrix populated by parameters, I actually have a stochastic matrix. So W is a realization of a stochastic matrix which depends on some parameters. And the key points to boost the computational efficiencies are two. Number one, I have a sparse matrix. So I have a bunch of zeros which are going to speed up linear algebra. And the second one is that the parameter space is going to be low dimensional. So I don't really have to deal with a large parametric space such as the one implied by all the entries of W at the same time. So this is going to boost posterior sampling if you are coming from the Bayesian perspective, and also sparse linear algebra is going to make everything much faster. So this is in general. Now I'm going to focus on the class of models that I will be talking throughout this talk, which is neural networks in time, and in particular this class of models here, which they have different names. If you're coming from the statistics literature, this is basically a state space model. If you're coming from the machine learning literature, you call this a long short-term memory process. But the idea is the same, really. You have you have a y, your output, which depends on some states h of t. These states want to account for long-range dependence with some parameter alpha here, and the real core of the model is here, where you're accounting for the input, which can be anything, the past observations, but also other covariates, as well as your state at time h of t minus 1. They all depend on these matrices w, w, x. I mix them together, I use a nonlinear operator, the activation function, and then I proceed describing the evolution of y of t. Okay, so the parameter vectors are these, and beta is easy. This is just penalized regression, lasso, ridge, bridge, elastic net, your favorite. The real issue is to estimate w and wx. And in order to do that in a timely fashion, I will do exactly what I said I would do before. So I will assume that w and wx are in fact sparse matrices, random realizations from sparse matrices. And this is the key idea of a class of models which have been developed about 10 years ago by Lukaszewicz in the machine learning literature. These are called issue-state networks. The idea, again, from a statistics perspective, is very simple. We use a spike-and-slab prior. So basically, we assume that every entry of this w or this wx that you can see here, they can either be 0 or not 0. So there will be a parameter pijw or pijwx, which is controlling the probability of this entry being 0 or not 0. If it is 0, fine. If it's not 0, it will be coming from some distribution f of nu w or f of nu wx, which is symmetric about 0, spike and slab. So 0 or non-zero with some sort of symmetric distribution, which can be uniform, it can be normal, it doesn't really matter, and as long as it is symmetric about 0. Okay, so this is, as you can, I mean, this is really fast, because now we can control the probability of every entry being 0, and it's typically, this probability is very high, 90–95%, and the other parameters are the other non-zero entries are realization from maybe a standard normal distribution, or maybe a distribution which is normal but for which you want to control the sigma square. Okay, so that was the vanilla version, the simple version. If you want to have the full equations of the deep models, this is what we do. So basically, we just keep iterating. We go deep into the process. We keep doing this process many times, and we have a deep issue-state networks, which is the one that I will be using throughout the talk. I won't spend too much time on this slide, because it's basically the same idea I've shown you before, except it's been done many times, d times to be precise. All right, so the main idea, if you want like a pictorial representation, it's this. So you have your input, which in this case is just the past observations here. They are fed into these random sparse metrics here, which in, again, machine learning literature is called the reservoir. And you, based on this random matrix here, throughout these linear filter beta, you are going to have eventually your description of y of t plus 1. Okay, and of course this depends on the w. Okay, because w is random, so every time you have a different realization, and every time you have a different y of t plus 1. So it's fast, but there is a price to pay. The price to pay is that every time this depends on the distribution of the w. And now, since it depends on the realization of w, then I can generate not just one forecast, not just one prediction, but I can generate an ensemble, a collection of predictions. And now the question is, okay, since I have this ensemble of prediction, is the uncertainty correctly quantified? In other words, I generate an ensemble, and I'm assuming that this ensemble is going to contain, say, 95% of the data, a 95% prediction interval. Is this really a 95% interval or not? So this is where we jumped in. So what I've shown you so far is basically stuff that's in the literature. And now, with one of my students, we started thinking about this problem, and we found out that in fact the uncertainty was not really properly quantified, and we needed to kind of provide some algorithms, some adjustments to the uncertainty in order to make sure that the forecast was calibrated. So we basically used the three very simple ingredients in order to do that. The first one is a very standard idea in machine learning, perhaps the simplest one. You split the data into a training set and into a testing set. Okay, so nothing spectacular here. In the second stage, we're going to do calibration marginally. Meaning we're gonna look at every single site, and we're gonna do some calibration in a way that I'm gonna show you in a second. And then conditional on the marginal calibration, we're gonna do multivariate or spatial calibration of the model using some sort of relatively simple geostatistical model. Okay, so by calibration here, I mean it in the probabilistic sense. So it means that if I have, say, a 95% confidence interval, 95% of the time, my prediction will be there. Okay, this is what I mean by calibrated forecast. Okay, so how do we do that? I'm going to show you some of the math here, not all of it because it's too long. And then I'm going to show you a few nice pictures that kind of give you the same ideas for those of you who, are struggling following the whole thing, which is admittedly a bit complicated for a short talk. So the idea is very simple. So we observe data up until time big T. Those are the training data. And then we generate an ensemble of forecasts from time t+1 to time t plus nw tau. So tau represents the lead time. So I'm going to make forecasts at time for 1 step ahead, 2 steps ahead, 3 steps ahead, all the way to tau steps ahead. And I will be doing this for sliding windows of length nw. What I will do next, I will group the forecasts by their lead forecasts. So basically, all the 1 step ahead forecast across these windows will be grouped together. And you can see here, this is this vector, which I will call FL1. The L stands for the vector element or the location for which I'm doing this. Those are separate L's. 1 is the lead time. So 1 step ahead prediction here. So I'm going to have, using this notation here, which means the forecast at time t+1 given all the observation up until time t. Then I'm going to have t plus tau observation, and I'm going to make a forecast at t plus tau plus 1, and I'm going to do the same all the way to nw minus 1. Same story here, except I'm making 2 steps ahead forecast, 3 steps ahead forecast, all the way to tau steps ahead forecast in this expression here. Okay, so I'm going to group basically together all the 1, 2, 3, 4, 5 steps ahead forecast. Why am I doing this will be clear in a second, but I'm collecting all the 1 step ahead, 2 steps ahead, and 3 steps ahead. So FL of J is the collection of J steps ahead forecast, when J is the lead time, and remember L here is the component for which I am doing this, this calibration. So I will be computing the residuals after I have that. So I'm going to compare this with my training set. I'm going to take my training set minus this vector Fj of L. And then once I have this comparison, I'm going to compute the standard deviation, which is another word for saying I'm going to compute the uncertainty around these forecasts that I have produced. And now comes one of the kind of key point of this algorithm. So if I want a forecast, usually it goes without saying that if I'm making a forecast for 3 or 4 steps ahead, this should be more uncertain than the one at 1 step ahead, right? The further I go in time, the more I would expect my uncertainty to increase because I have less information, right? So what I will do after I've computed the standard deviation at the different steps ahead prediction, I'm going to fit a monotonic spline. So I'm going to smooth the standard deviations by assuming that the standard deviation will increase. So I want them to be smooth, but I also want them to increase because I expect the uncertainty to be always increasing as I make predictions for something further and further in time. So I'm going to fit a monotonic spline. I'm going to standardize the data now. Now I have the standard deviation. I divide my observations by the standard deviation, and then I'm left with this model here. So I'm going to look at the problem now jointly, so all the vectors together, and now I'm in this situation where my standardized residuals now will be IID from some multivariate normal distribution, mean 0 and variance C. Now, this is a covariance structure. You can fit your favorite spatial model. You can fit graphical lasso if you like. If you have a vector dependence without spatial information. There are all sorts of methods, geostatistical methods you can use to fit the spatial model. I won't talk about them because again, that's not it's already enough information. All right, so if I lost anyone, you know, we can restart here to kind of give you an idea with these pictures. So what I will do is the following. So step number one, I'm going to produce the forecast. So what you can see here, those histograms are the ensemble predictions based on this issue state network model. Y of t is the actual observation, the one in the training set. And you can see here that there seems to be a mismatch here. And of course, since the ensemble has a lot of data, I'm going to need to estimate the standard deviation. So the next step is looking at the residuals here, the difference between the actual true value and the ensemble prediction. I'm going to compute the standard deviation or the variance, which is sigma hat square 1 all the way to sigma hat square k, where k is the k steps ahead prediction. So I have computed these variances here, and I'm going to smooth them using a monotonic spline. Because again, remember, I want my uncertainty to always be increasing in time. And finally, conditional on this, I'm going to fit a spatial or a multivariate model. So that's my last step, okay? Now, all these procedures assume that things are Gaussian, and we have also provided the other algorithms with quantile regression, which account for the fact that the data may depart from Gaussianity, although not dramatically. So in a nutshell, this is the algorithm that we proposed. We provided some simulations according to the Lorentz 96 models, which is basically one of a very popular model in climate science because it's a good representation of like a system with an attractor, which again, some people say it's basically how you should represent the climate. And we generate data from here, and we wanted to test our calibration approach and our prediction approach of the issue state network compared to other models which have been out there. So here you can see the equation of the Lorentz 96 model, and here you can see just an example of one realization for one element of the Lorentz 96. So as you can see, there are some patterns here. There is some oscillation, but the oscillation is not exactly regular. And that actually is why do you need this kind of neural network models, because there is some pattern here, but it's not super regular. If it was super regular, then all you need is a sine and cosine, and then you're done. So here it's a bit more complicated than that. So these are the point forecasts, so mean squared error. And you can immediately see here from this table, I mean, we tried all sorts of things. We tried deep issue state network, shallow issue state network. We tried RFEMA, state space models, VAR models, hidden Markov models, long short-term memory, gated recurrent unit. Those are other machine learning models in time. All of them give a worse mean squared error than the deep issue state model. In parentheses, you have the standard deviation across the multiple sites. And again, you can see that it has a pretty low variance. So this deep issue state network model for the Lorentz 96 works extremely well. And here you can see just an example of one site. So what happens, those are the true value in solid black, and the deep issue state network is the one that is dashed here. Okay, so some are models like the RFEMA model here, which is very popular in standard time series modeling in statistics, is basically hopeless. It's just trying to predict a flat line. Whereas this deep issue state network model is capturing this kind of long range dependence from the Lorentz 96. Now, in a picture, this is what's going on. So I'm going to fit, this is again from the Lorentz 96. This is my monotonic spline. What you can see here is just, again, another representation if you're familiar with probabilistic forecast on how on how these things work. So you can see here, this would be something called the probability integral transform, which is flat if the forecast is calibrated. So if the 95% confidence interval were to include 95% of the time the true value, then you would see a flat line. And this is the calibrated method, so it's close to a flat line. Whereas if you were to take the original data, you would have this U shape, which is, you know, again, a flag that something is wrong and your uncertainty has not been well calibrated. Okay, so also another thing that I wanted to highlight, if we use the calibration, I'm going to show you the numbers in a second, but I hope you can appreciate here. I've taken the same location that I've shown you before for the Lorentz 96, and I've just shown you here the results for the issue state network, how the uncertainty here is small, and as you go along, the uncertainty actually increases. So this idea of the expansion of the uncertainty is also quite easy to appreciate graphically, okay? And that's something that, as I said, we should expect, because the further along we are in the prediction, the more uncertain my prediction should be. Now, if you want to have a few numbers, check the time, okay, I'm well on time. Uncertainty quantification wide, what you can see here in this table, these four numbers represent the uncalibrated versus the calibrated approach. So remember, I'm generating 95% confidence intervals, and I know that, you know, if everything works well, on average, I should have 95% of my observations here. And if I don't calibrate, I have 77. Whereas if I calibrate, I have 94.5, and this is well within the standard deviation across all the different sites of the Lorentz 96. Also, if I do this kind of joint calibration at the end, if I assume that I have independent data, my coverage is going to be 100%, which is not a good thing, because in a 95% confidence interval, I want 95% of the time the true value. Instead, I have if I do it in a dependent case, this is going to be smaller, almost 92, but remember the standard deviation here is large enough, so it's within the 95% or almost, depending on, you know, if you take 2 sigma. Okay, so at least it's a bit better. Okay, so I want to show you now the application. Those are all simulated data. We took air pollution data from PM 2.5 particulate matter. It's an indication of how much air pollution there is in San Francisco. We choose San Francisco because there are lots of people which have these sensors. So people have, you know, lots of people with houses in which they have these private sensors which they can collect air pollution. We have 44 of them, and we took observations from 1st of January 2020 to 24th of May 2020. Now, why have I chosen these dates? For 2 reasons. First of all, these sensors have been available only for the past few years, and at that time it was basically, you know, we started doing this work at the end of 2020. The second reason is that I wanted to avoid the fire season, and which starts at the end of May. And if you have fires, then all the analysis is it's impossible to forecast fires, because suddenly you have a behavior and that is due to how the city works, due to traffic and everything. Then comes a gigantic fire, and, you know, the values goes up the roof, and of course your model, no model can capture them. So we decided to forecast just before the fire season started. Now, one thing that I want to address before I show you the results, I've shown you some results on the deep issue state network versus the shallow issue state networks, and you have seen that the deep model is actually working very well. We know that asymptotically doesn't matter, because there's something called the universal function approximation, that basically any function can be approximated by a neural network, but this is just true asymptotically. In practice, do we need a shallow or do we need a deep model? I know this is a very general question, and I don't want to kind of go through all the details here. I just want to kind of give you my 5 cents on the data that we have seen. So if we were to do a table, you know, do we really need a deep model? Can we get away with a shallow model if we were to do some cross-validation? What is the advantage of having a relatively short but deep network versus an incredibly long but shallow network? Which matters the most? And to us, I mean, we were pretty satisfied with these results. So what you can see here are cross-validation results. These are the number of nodes, so the width of the network versus the depth of the network. And as you can see, if you have a shallow network, things are not terrible, but you can see that once you increase the number of layers, the numbers, especially for very short network, goes down pretty dramatically. And the other results are pretty stable. So that means that, again, as you go deeper, at least 1 or 2 level of depth will give you a fair robustness with respect to the number of nodes and overall good results. Okay, so you can still get decent results for a shallow network, but you need a really shallow, really large one in order to achieve some form of flexibility there. Okay, That's it. That doesn't mean it's true always, but for this data set, we saw this. Now, what you can see here is the same plots as before, except before were simulated data. Now this is San Francisco for one location. Those are the predictions for the 20th of May, 2020 to the 24th of May. Those are 4-hourly data, so data aggregated every 4 hours. This is the PIT, the original one, so the one without any calibration. This is the adjusted one, which is clearly more flat, which is again an indication of the fact that we have calibrated our forecast. So the uncertainty is properly calibrated. Again, the prediction is similar table as before. You can clearly see that the deep issue state network is by far the best model. And here we've also tried some geostatistical models called fixed rank rigging. There are other types of geostatistical approaches. It doesn't really matter what you try, the deep issue state network was always consistently the best model here, both in terms of point prediction, but also in terms of precision. Overall, through the site, you almost uniformly through the site, we have better results from the deep issue state network. Uncertainty, same story. Marginally, we had a coverage which was 99 if it was unadjusted, or spot on 95%, or almost spot on. It's perhaps even more interesting, this one here. If you do the average, so if you want to do a confidence interval, the average of the air pollution across all locations, and you don't do a calibration, so you assume independent locations, if you want to have a 95% confidence interval, you cover it only 44% of the time. So you have a gigantic under coverage. If instead you do a spatial model, then you have almost the correct amount, so 94.4%. And bear in mind that calibrating the mean, the average of a spatial process is an extremely complicated task to perform. It's very, very hard to model uncertainty correctly at different spatial scales of the process. Okay, so once we have this model, we can do all sorts of interesting things. Now, we were interested in understanding the exposure to air pollution. In particular, we kind of cross-referenced this data with the population in San Francisco. And we wanted to understand how many people were supposed to be exposed to air pollution, which could be harmful. So we gave a threshold, in this case, 12.1 micrograms per cubic meter, which is supposed to be harmful for vulnerable individuals. And we forecasted how many people in San Francisco would have been exposed to this harmful amount of air pollution over the next few days, and especially where, because we can also give this kind of spatial information. So especially in this part of San Francisco, because again, the reason is that, again, this is the San Francisco Bay. We try to come up with an explanation. You know, there is more traffic in this area rather than in this area, and the wind typically blows into this direction. So this was our explanation. But again, we haven't, I mean, it would require an analysis of multiple years to kind of, you know, be confident about this. And we didn't have multiple years because data collection started in 2020. Okay, so that's all I wanted to talk about issue state networks. We have been working on a couple of generalizations. One is a spiking neural network, which is another type of recurrent neural network, which is used for time series forecasting. The key difference is that we convert the data into binary sequences, the so-called spike trains. And these spike trains are used as input for a model. So we're really trying to replicate what the brain does, okay? So basically the brain communicates into spike trains, and it feeds a network, your brain, and it then shoots those spike trains into other neurons, okay? So this is a fairly popular type of neural network. Again, it's not super new. It's something that's been out there for quite a while. We've been trying to replicate this. If you want to have some idea of how does it work, it works exactly as the brain works. So it accumulates electrical potential, and then once it reaches a critical threshold, it spikes, and then it goes to rest. Okay, so it accumulates again energy potential, it spikes, and it rests. Okay, and this results into a binary sequence of output spike trains. So you convert this sequence, these numbers, these continuous numbers, into a spike train, and then you feed it into the network. So we've implemented spiking neural networks, and we have used them in conjunction with issue state network. So there are both methods. They fall within this kind of broad umbrella of reservoir computing methods. This type of method with spiking neural network has a name. It's called liquid state machine. And we have used both of them in conjunction into a single model, issue state networks and spiking neural networks, to understand whether there was an improvement in predictability. And we found out that basically a model accounting for both is faster and, sorry, not faster, it's more accurate than using them independently. Now, why are we doing this? Because remember, our final aim is to calibrate the final product. So we're not claiming we're doing this just because it's a new model. This is not a new model, but we're looking at this from the probabilistic point of view. Finally, the second extension, which is again should be to honor the name of the seminar series, physics-informed neural networks. We are using these methods also to minimize loss functions to optimize a physics-informed model. So right now I've done inference by back propagation or cross-validation. The goal is to minimize some sort of function, is the mean squared error. However, if you have some physical information, we want to have a forecast which is also compliant towards the laws of physics, which are typically described from a partial differential equation. So our contribution, this is very new work. We're almost done with our first paper, is really to contribute to say whether we can calibrate a model which has this double reservoir structure that I've shown you before, but it can also be calibrated with a physics-informed approach. So what do I mean by this? Is that I will be using a minimization of two cost functions, so it's basically a regularization problem. The first cost function will be the usual one, the fit, the mean squared error of the forecasted points against the actual data. The second penalty here is the physics penalty. So how close is my forecast to some PD, which is describing the process, the model, which is describing the data, which is describing the physical process that is going on in my analysis. So we tried some experiments. We focused in particular on fundamental PDs in fluid mechanics. We are currently working with Navier-Stokes, three-dimensional, but we did some toy examples with a one-dimensional version called the Berger equation. The Berger equation is basically a one-dimensional flow which has a certain viscosity, and we perturb it at the initial condition, and then we see basically how fast it goes to rest. And of course, that depends on the fluid viscosity. So this is the Berger equation. So it's basically derivative in time here, and then we have it's almost like a diffusion reaction problem, diffusion transport problem. Sorry, except there is this U term here which makes everything nonlinear. Okay. So if you want to have a picture, this is how the Berger equation looks like. So we give an initial condition of a sign, and as you keep mapping it in time, you see that this sign kind of dampens because of the viscosity because of the fluid. Okay, and how fast it dampens to zero depends on the viscosity of the fluid, which in our simulation we choose it to be 0.01 over pi. So 50 spatial locations. This is how the Berger equation looks like. So X is here, T in time. You can see here the sines and cosine, they go up and down. And then as time goes by, the fluid kind of goes back to its equilibrium because we're not really stimulating the fluid. We're not having a force in our PD. So some of the preliminary results, so this is stuff that's really, really new. If we were to use a deep issue state network, we're going to have a 9.229 mean squared error. If we're going to use a reservoir and if we're going to use spiking and deep issue state networks, so deep spiking and deep issue state networks, we're going to have about 13% improvement with respect to deep issue state networks. If we use a PD penalization, and you can see this in this picture here, this is the picture of the PD of the root mean square error, of the mean squared error, you can clearly see that there's going to be an improvement of 26 and 15% with respect to the deep issue state network and also with respect to this double reservoir model. So uniformly, we have better results if we are to inform our forecast with the PD. Now I'm cheating here because I'm generating the data from the Berger and then I'm penalizing them with respect to the same equation. So, I cannot expect very, very bad results here, but now we're performing, an actual case study with high resolution wind and Navier-Stokes in 3D, where we hope results will be more realistic. So anyway, wrapping up. So I'm not claiming I have invented the dynamic neural network. They've been around for more than 20 years in computer science. I think our main contribution on a very broad level is that these reservoir computing approach, they're usually envisioned as a workaround for stability issues. So vanishing gradient, exploding gradients, all these techniques. The way I look at this as a statistician is more from a model-based perspective, meaning that the algorithm doesn't matter too much. To me, what matters is the model for which you seek the inference. And the model is a probabilistic model. So as such, you need to quantify the uncertainty. And we provided a way to calibrate the uncertainty correctly. So to correctly do uncertainty quantification. And finally, and this is the last part of my talk, I also explored, we are in the process of exploring, how does this process of good uncertainty quantification be transferred not just to issue state networks, but to more sophisticated reservoir computing approaches, and perhaps most importantly to this very popular class of models, which is called physics-informed neural network, which the past 2-3 years has kind of exploded in machine learning as one of the most active areas of research. So that's it.
Thank you very much.
Thank you.
Thanks a lot for sharing your work. So I'll open the floor to questions if we have any. We have some clapping too. So you may ask your questions by asking in person, or you may type them directly in the chat box. In the meantime, maybe I can ask one question about I believe
Carlo, I see one raised hand.
Oh, sorry. I thought it was a clap.
Sorry. Just a quick question. Out of curiosity, you mentioned that the data taking period was basically kind of almost the first half of 2020. Did the COVID lockdowns disrupt significantly that data? Because I would imagine that there would have been a switch in, let's say, normal patterns of traffic and say
right.
around.
Right. So we have written a paper in the Lancet on this, but it's for China and Europe. In reality, the little data we had in San Francisco, the patterns were not terribly altered because the traffic was not dramatic to begin with. So you see we saw dramatic shifts in China where the amount of traffic was much higher than the government kind of went very hard on the lockdown and people didn't use cars. But in San Francisco, we didn't really see a gigantic dramatic shift.
Interesting. I also want to say that excellent presentation. It's one of the best I've seen, super clear, really to the point and really well explained.
Okay, well, thank you very much. Appreciate it.
Thank you for the question, Carlos. Any more questions? I was simply going to ask about.
No, I have one. I see Kutai here.
Oh, I'm thinking there are claps. Sorry. Go ahead.
Thank you for the presentation. It was a great presentation.
Sure.
At the beginning, when you were explaining the echo state networks, you mentioned this kind of Bernoulli distribution for zeroing out, slab and spike and slab. So in this case, how did you choose the phi W's?
Cross validation.
Cross validation, but
cross-validation.
What was the metric for cross validation? Because
mean squared error. We use that. Yes.
Because zeroing out some weights, conceptually, intuitively right now, should decrease the performance, right?
Yes.
But if you cross validate only by looking the mean square error, I guess the pi's should go to 1, right? They should always give 1. For cross-validating and incentivizing this dropping out or slabbing, I think shouldn't we need some sort of sparsity incentivization or uncertainty incentivization?
So not quite. And the reason is that we are not assuming that those weights are fixed. If they were fixed, then it was a different story, because the more fixed weights you have, the more flexibility you have. Even if the probability, or even if we had a full matrix, we would still have independent realizations from some distribution. So the model doesn't get more flexible if you have a full matrix.
Okay.
Because again, it's all stochastic here. Okay. So yeah, I mean, and actually it turns out it's I mean, once you go to 90% of zeros, it's fairly insensitive towards that. So it's in some extent is very different from dropout. So dropout is like, you know, it's knocking off fixed deterministic terms in order to do this kind of UQ. Here, I'm assuming that the parameters themselves are stochastic rather than knocking them down inside the deterministic model.
I see. Thank you. But did you check the final probability of sparsity at the end, because they might end up very high, these pies also, right?
They are 90%, 95%. They are pretty high. And that's exactly the point. You know, the high, so they're fast. Of course, it's not going to be as precise as long short-term memory. But we want something with UQ. So I'm willing to pay the price on something slightly less precise, but it gives you correct the UQ.
Okay. Thank you very much.
Sure.
Thank you, Peter. We have a question from Peter. Yes, I did not miss this one.
Hello. Thank you very much for the presentation. I have a quick question about the physics penalization. So at the moment, you're doing it just point-wise. So you're saying that point-wise, the solution should incur some penalty for deviating from physics, more or less. Yeah, here with MSE. But, you know, can you somehow incorporate the boundary conditions, for example, exactly so that any generated, so that any network would at least satisfy the boundary conditions of the physics?
I mean, again, in its full form, yes, but I only have 45 minutes, so I didn't want to kind of get into that. But I mean, there are ways to account for that. I mean, in fact, one of the work I'm doing right now is without using neural networks. It's more like a functional approach. So I mean, can you actually penalize the integral of in a functional space, and this functional space has to account for Dirichlet or Neumann, or, you know, your favorite boundary condition of the problem. So yes, of course it can be done. It has been done in the machine learning literature, and I'm working on like more like the functional version of it.
So
the only reason you see this slide in a kind of very quick form, because I didn't know how many people are familiar with physics informed neural networks, so I didn't want to throw too much stuff on initial conditions and boundary conditions.
So just to get this straight, you can guarantee that your neural network belongs to a certain functional space. You can tweak it in such a way that you guarantee.
Well, if you close, like suppose your function is in L2 or in some Sobolev space, then you can close the Sobolev space with respect to a certain boundary condition. Now, we haven't worked out the theory for every single case, but it's certainly the Dirichlet conditions. They're fairly easy to enforce. You just close the Sobolev space with respect to the zero, the functions which are zero at the boundary, and that's it. So it's a Hilbert space. You can do all sorts of things, and you can use you can prove uniqueness. You can do all sorts of, or you can also get pretty nice theoretical results.
Thank you very much. Thank you for the talk again.
Sure.
Thank you very much, Peter. Any more questions? All right. I had one small question. I don't know what I can ask it, but it's just about extreme events. So in terms of your the calibrated model, how does it cope with noise signals? So very noisy signals, such as, you know, extreme weather events that are, at least for me, I always have this problem when my training data is contaminated with some extreme signal. It's always obviously problematic for the forecast. So how do you deal with this?
So this the model, the calibration approach I've shown you here is the one where we started. It was a first-year student my student was a first-year PhD student when he started. So we started with something simple on the Gaussian case. We have worked out a non-Gaussian version with quantile regression, and I think that would be my best answer right now. So if you deal with quantile regression, it's a bit more flexible, so you can account for some departures from Gaussianity. Now, the question is whether is it a departure which is large enough to justify extreme value theory? To incorporate extreme values. That I haven't checked. What I do know, however, is that people are moving away from, at least in modeling. People modeling extremes are kind of more and more skeptical towards like generalized extreme value models or max stable processes, which are supposed to be very unflexible computationally. So people prefer to use this kind of non-Gaussian models to begin with. So this gives me confidence that even with quantile regression, you can capture, at least to some extent, this behavior and the calibration of extremes. But this is all speculation at the moment. I don't have any numerical evidence for that.
Of course. No, thank you. Thanks. I appreciate that answer. And also with regards to the second part, physics information neural networks. So one thing sort of like I like to ask a lot about always with regards to this topic is about interpretability. And one downside I always see with physics information, so pins is like one of the many ways of incorporating physics in machine learning. I still find that pins themselves are quite still not interpretable, because you don't get any information insight about the governing dynamics. So you cannot really recover, your state dynamics. And so I was wondering if you had any considerations about, this aspect also.
So the problem, I don't think it's the problem of the physics informed neural network. The problem is the neural network. So, the neural network is not interpretable by nature. So what do we do with this? I can offer two options. Option number one, do explainable AI. So there are Shapley values and other approaches. We recently wrote a paper on this for environmental statisticians. There are ways to linearize the local solution of a neural network so that at least you have some idea of the contribution of the different inputs. So you recover to some extent the interpretability by doing some explainable AI on top of your physics physics informed neural network. The other solution I can offer is, this principle of physics informed neural network doesn't really have to be a neural network. The principle of penalizing inference or learning, if you like, from using a PDE can be done with any type of model. So if you think neural networks are too uninterpretable, use a linear regression. You can get away with doing the same thing using linear regression. You're going to constrain the parameter space, and you're going to have something which is a compromise between the fit and the PDE. And maybe it will work. Maybe linear regression is too simple. Then you want to use maybe something in between neural networks and linear regression. So like, I don't know, support vector machines or random forests. There are many methods which are more interpretable. And again, this principle here, it's so flexible it can be used to any model. Right.
Okay. No, thanks for that. The reason why I ask this question, and I like to ask these questions, is because I feel like as a platform, as a field, these questions need to be asked, because if they're asked, then of course we are, even just like what you've just done now, right, by on the spot trying to think about, hypothesize about how we could improve these. I think it's part of the discussion that needs to be had, and I'd like to take advantage of this platform.
Yes,
that agenda.
And I agree with you in that sense. It's not going to solve the interpretability problem. There is another problem that maybe I would like to just mention here. This idea of penalization of the physics is fine, but you are assuming that you know the correct physics. Exactly. And maybe for physical problems, it's fine. For Navier-Stokes is fine. If you're studying like high dimensional fluid movement, then Navier-Stokes is fine. But there are so many other problems in which the physics or the dynamics of the problem are just not well characterized.
Yes,
and in those cases, maybe you have competing physical systems. What do you do in that case? So it's not, it's nice as an idea, but it's not going to solve every problem. And I mean, we're at the early stages in this. As we keep digging in this, I'm sure we'll find ways to compromise this. But you know, there is a lot of work to be done here.
There is some interesting work actually going on about discovering differential equations that, you know, about real systems. I know that there are certain decomposition methods that are being developed, and also there is certain deep learning methods that combine things like SIND, which is like a decomposition method for sparse data, and also combined with deep learnings. And I know there's one paper, I can't remember the name of the authors, that discover certain, so they, you know, they replace, they include the known terms of from the principles of physics, and then add these unknown terms, which are universal approximators, deep learning, and somehow figure out in a sort of linear addition combination, you know, there are other terms that that maybe in a way discover some form of new fitted differential equation to the actual system. But anyway, there's a lot, so there is some things going on, and I think it's an interesting direction to go in. But then you always have to compromise on certain things like interpretability in this case.
Yes.
So anyway, this is a kind of a discussion that maybe we can have one day in person or at a conference, hopefully, if we come to a point where we can organize one. Right, I'll stop here. I'll say thank you to everyone that has joined. Stefano, thank you so much for sharing your work with us, and for your time after all. And I'll see everyone in 2 weeks' time. Thank you very much.
Thank you. Bye-bye.